I'm a huge Ben Eater fan and have watched almost all of his videos. But it's only until recently that I've decided to start building some of his projects. Um, I've been into electronics for a little while, so I have quite a collection of chips already. So in some cases, I'm building things a little differently than he built them, and in some cases, I'm doing that in order to in order to make things a little easier on myself. So, for example, my first project was his clock circuit, which, if you're a Ben Eater fan, you'll recognize this board. Um, I've done almost everything just like he did, with some minor exceptions. Um, Instead of a 1 mega ohm resistor here, I'm using a 100K resistor. And then corresponding, since the resistor is smaller, this is a 10K, or sorry, a 10 microfarad capacitor instead of a 1 microfarad capacitor. I've also found on Amazon for relatively inexpensive these potentiometers that are designed to fit into a breadboard and have a little knob on top and make adjusting it quite easy. Another small change I made on this board was in these buttons. He had in his video an on-off button that he had to solder to some jumpers in order to make it fit in the breadboard. And instead, I've just used these push buttons. And because this is the monostable circuit, which if you've watched his video on building this board, you'll know that that means that you can set it, bistable circuit, which means you can set it to either high or low, and it'll stay in that state. And so I just have these push buttons, so it's a little easier than the on-off button that he was using. It's a little less expensive because I already had these in stock, so I didn't have to go buy anything. And also, you can just push one or the other button. Here I've labeled them so I know which one I'm using, either the clock or the step. And this is the step button here, so I've labeled that as well, step. The only other difference I've done here is that instead of a wire connecting the halt line to the AND gate, I have used a 4.7 kilo ohm resistor. And the reason I've done that will become clear later in this video, but basically it's so that I can override the halt. So I can have a signal that comes in, and I'm going to want that signal to come in directly because it is a negative signal. So this will be held high, and so this AND gate, this is an AND gate, and so this AND gate, this will be high. So when the clock pulse is high, then the clock will output. So I can show you this in operation. Let me hook up and just show you that it works as expected. So right now it's not doing anything, and that's because it's in step mode. So if I press step, you'll see that it pulses. If I switch it to clock, you'll see that it is working with the clock, and that's adjustable to as much as I want. So that's just the basic Ben Eater clock circuit with some very minor changes to make things a little easier for me, and so that I can use parts that I already had in stock. The reason I built that first is that I wanted to build Ben Eater's World's Worst VGA card, and that's why this is titled World's Worst VGA Card Revisited. So here is my start on that card, and I've made quite a few differences here. My goal with this card is I want it to fit on 3 breadboards instead of the 5 that Ben Eater uses. So how I'm managing to do that is that I am, let me give you a close-up on this board. how I'm doing that is that I am using, if you can see over here, 74 HCT 4040 chip. HCT series are CMOS chips that use less power than the LS chips that Ben Eater uses, and they're also compatible with both TTL logic levels like the LS chips, and they're also compatible with CMOS level chips like the HC series, which you'll see that's what I have. That's what I'm using here. So this chip, the 74 4040, is a 12-bit counter, which is exactly what we need. So where Ben is using 4-bit counters, I'm just using a single. I'm just using a single 12-bit counter, and that has more than enough bits because if you've seen the video on the world's worst video card that Ben made, he'll need for the horizontal sync he needs 9 bits, and for the vertical sync he needs 10 bits. So we have up to 12 here, so we're in good shape. There is a difference between this and the chips that he's using, and that's that the reset on his chips are reset when this line goes negative, and this chip is reset. You can see there's no bar over this on pin 11, and that means that this reset is going to happen when this pin goes high, and that's verified in here. It says here. A high voltage level on MR line resets all counters to their 0 states. So that's going to make a little bit difference later on when I show you this circuit further on here. Let me get back to video. So so that's this chip. It's a 12-bit counter. This is Q0. It's laid out a little strange. Q0 is right here. And then, or that is say the 0-bit. And then here is the 2-bit, the 3-bit, the 4-bit, and then it goes to the 6-bit, and then to the 5-bit, and then the 7-bit. And then over here is the 8-bit, 9-bit, and then the other bits are here, here, and up here. We won't be using those for the horizontal sync board, which is the only board that we're going to get started with. Another difference I'm doing to save some space on the layout, and also because I didn't have a oscillator can that you can just plug in and use as an oscillator like Ben did. But what I did have was this 10 megahertz crystal. So this is a 10 megahertz crystal, and I've created an oscillator out of it very simply. It's very easy to do. You connect two NOT gates together, and then both of them you feed back with a resistor. The exact value doesn't matter. I'm using a 1K resistor in this case. And let me show you the circuit for that. So what that circuit looks like, you have two NOT chips, or NOT gates, I mean, single chip. And you connect the output of one to the input of the other. And then you connect a resistor from the output of one back to its own input, and you do that for the other one. And I'm using, in this case, it's a 10 megahertz clock, if you recall, from Ben's video. So I'm using 1K resistors, and that seems to be working. 1K, 1K. And then to make it the right thing, I have a 10 megahertz crystal here. This makes it the right frequency, 10 megahertz. So that's the frequency we want. The 10 megahertz crystal makes this whole thing oscillate at the crystal frequency of 10 megahertz. And we'll take a look at that. All right, so the rest of the circuit is very similar. So there's two chips with 6 NOT gates on them. And so I've wired everything up to those NOT gates. And then by running the appropriate wires here, I'm using blue for 0 or ground or low. and I'm using green for 1 or high. And I've wired up each of these chips, and these are these are 8-input NAND gates, just like Ben uses. I've done something a little different. Ben wires these LEDs so that they light up when there's power to the when the output is high. But since these are NAND gates, the way this works is they stay high until you hit the number, and I've labeled the numbers here so I can remember them. So when this one hits 200, then the way Ben had it was this would stay lit until it hits 200, and then it would be dark, and then it'd go back to being lit. And same thing, 210, 242, and 264. That's fine, but I wired mine differently. What I did was I flipped the LED around and I put the positive input into the 5-volt connection, and that way these will light up when this pin goes low, and that's great because now you're going to, instead of see it blink off for a second, you'll see it flash on. And if I plug this in, you won't really be able to see it. You won't be able to see them flash on. They'll just look like they're dim, and that's because they're lit occasionally. Now, one of the differences I told you about was with the 744040 chip, is that the reset, which is this pin here, will go has to be set high to do the reset. So here you see that I've got a 4.7 K resistor here. Pull this out, always you can see that 4.7 K resistor there. And that resistor holds the master reset low because it's plugged into low. So that'll hold it low until it's forced high. Now, because this is a NAND gate, an 8-input NAND gate, this is going to be high all the time and then go low when this number is reached. And so what I've done is I have a spare. Fortunately, there's one spare NOT gate on this after I've used 2 for the clock, and we need 9 for the counter, so that leaves 1 left. So we've got this NOT gate, so I have it run to this NOT gate and then back over here, so that this goes positive when this one goes negative. In other words, this goes positive when the LED is on, since the LED goes on when the output is low on this chip. I said negative, I meant low. So so this looks like it's working, but the real question is, how do we know that these are flashing when they're supposed to flash? Now, Ben's solution was to take a $700 signal generator that could count the pulses, and he would stop these when he would stop the count at the appropriate number, and you could see that the LED in his case was off, or in my case it would be on because of the way I wired these LEDs. That's great if you have a $700 signal generator, but I don't have a $700 signal generator. In fact, I don't have a signal generator except for one. I have the Ben Eater clock circuit. Fortunately, the Ben Eater clock circuit, he had the forethought to include a halt line. So that is why I added this resistor here, because I need to be able to change this pin using a negative signal instead of a positive signal. So his is set up so that it goes through this NOT gate. And so when this is, let me turn on the clock. Let me plug it in so I can show you. So he has it set up so that when this pin goes high, then the clock stops working, stops running, and when it goes low, it runs. But the output from these chips is going to stay high and then go low. So I want to plug these in directly to I'm going to want to plug the output of here directly into the input of here, because I am going to the input of the halt, because I am going to use that board to do the counting. So how am I going to do that? Well, I built this board. Now this board is very similar to the horizontal sync in that it has a 74-40-40 counter chip, 12-bit counter chip. And I'm only looking at 8 of the bits at a time here. So I'm only using 8 of the bits, but they are wired in so that they go just like in the horizontal sync board. Each bit, output of each of those bits is wired into one of the inputs of sorry. Let me start that again. The output, each of these outputs of these is wired into the input of these chips, which these are XOR chips. So what is an XOR chip? We haven't talked about those before. XOR is exclusive OR. And how it works is exclusive OR. How exclusive OR works is if both exclusive OR, yeah, if both inputs are low, then the output is low. If both inputs are high, the output is low. If one of the inputs is low and the other input is high, then the output is high. So what we want to be able to do is we want to be able to set a point at which we want to count to, and then we want to be able to count up to that point, and when we get to that point, we want to halt the clock. That's what Ben Eater was doing with his video, with his fancy signal generator. It would run to a certain number of pulses. He set how many he wanted, and it stopped pulsing when it got there. So we're going to do that same thing. We want to, if you look at the clock board again, what we want to do is we want the input here, this input, to go high when we're done counting. That's what we want. Sorry, we want it to stay high until we're done counting, and then we want it to go low. So we want this to be high while it counts, and then when we get to the number of pulses that we want it to stop. So what this circuit does is it does the counting, and here you can set how many pulses you want it to count up to by setting these switches. Let me give you a close-up of that. These are called DIP switches. DIP stands for dual inline package, because that's what these packages are, dual inline. There's dual inline pins. And you can set each one however you want. And the cool thing about these is that they fit nicely on the breadboard, just like a chip does. Now, what we want to be able to do is be able to say, set these pins, set each of these switches to a value that represents a binary number, and then we want this circuit, the output is here, we want this to stay high until we reach that number, and then we want it to go low. And that's where these chips come in. Now, to do that would be really easy if I had these XNOR, exclusive NOR gates. So these work like what I showed you, only they work, hey, if both are low, then we want the output to go high. That sounds like what we want. Like if we want it so that if a bit in our counter matches a bit in our switch, then the output should go high for that bit. So how that looks like, what that would look like is this. This is the symbol for an exclusive NOR gate here. And I've lost my pointer. There it is. This is the symbol for an exclusive NOR gate. And what we want is if a given bit, which I represent by QX, Q is means a bit, and X means it can be anything from 0 to 7. And so if one of our bits is an input to exclusive NOR, and then we have this switch set up so that it's normally ground, but if we turn on the switch, then it'll represent a 1. So this will be high if the switch is on, and it'll be low if the switch is off. And so if that means that if, let's say, QX were high, then and the switch were closed or on, then that would be high, high, and the exclusive NOR means that this would also be high if you remember the output. High, high means high. Likewise, if QX is low and the switch is off, then this is a low. This is pulled low by this resistor. So this is low. So that's a low, and this is a low. And if we look at the logic, the function table, you see that if both inputs are low, then the output is high as well. And if they're different than each other, which would be represented by if the switch, for example, were open and Q were high, then they're different than each other, and this would be a low. So that's ideally what we'd have. But the problem is I didn't have any X NOR gates on hand. They're easy enough to get. They're cheap enough, but I just didn't happen to have any. What I did have was plain old XOR gates. So an XOR gate is symbol is similar, but you can see that it doesn't have the inversion symbol here. And so the function table for that is that if A and B is low, then the output is low, and if they're both high, then the output is low. But if they're different, then the output is high. So if we simply rewire the switch like this, so like hold on, if we simply rewire the switch like this compared to the other one, you can see on this one it's normally held low, and if the switch is on, then it goes high. And that's kind of what you'd normally think. Like I turned it on, so it should go high. But we need to invert that. And my first thought was, oh, I could just use an inverter, but that's a whole other chip, which frankly won't fit on the board. So instead, I simply made the switch into an inverter by tying it high normally. Now this is normally high, but when the switch goes on, it goes low. So this is kind of like a NOT circuit for the switch. And so you can see now that if a bit QX, say it's Q0, if that's high, and the switch is closed, well then with our XOR, let's say this is A, let's say the QX is input A, that would be high, and the switch is on, which makes it go low, and that means the output would be high. And that's what we want. That means, hey, it matches. When that matches, we're going to want to, well, when all the bits match, we're going to want to stop the clock from running. So if we look at it again, we look at if this, for example, if this were low and the switch is off, then that means this one's high. And again, wrong one. There we go. So if one is high and one is low, then it's high. So that's what we want. So this is the circuit that I wired up. So the only thing left to do is to do the comparison. So you can see each bit of the counter is wired to one side of the input of these quad XOR gates. So that's bit 0. Bit 1 is here. You can see that's wired to that gate. And then bit 2 is wired to the next input. Bit 3 is wired to this brown wire here. Bit 3 is wired to is wired to the first input of this second chip, and bit 4, which is this one here, is wired to the first input of the second XOR gate on the second chip. And here is pin 6, and it's wired to the third gate, if you will, on this second chip. And that's pin, let's see, oh, this is pin 5, and it's wired to the last gate on the first chip. And then here's Q7, and it is wired way over to the fourth input on the second chip here. So that takes care of all of those. And then on the switches, you can see for each switch, I have wherever a wire is connected, the switch wires are gray, and you can see wherever one of those is connected, I've connected it to high with a 4.7 kilo ohm resistor. Again, high, these are tied high. You can see they're all tied to the wire. And then where each of the switches on the other side of where the wire is, where the switch would connect, I've wired those to ground. That's why these are black, and you can see they're wired to ground. So that wires up each of these, and we could follow those like we did for the other one. Pin 0 runs all the way over here to the opposite of Q0, and pin 1 here runs all the way over here to the opposite of Q1, and 3 runs all the way over here to the opposite of I'm sorry, position 2 is here, runs all the way over here to the opposite of Q2, which is right there, and Q3 and so forth. Like these are all wired to the matching one. And then finally, the output, the orange wires are the output here from each of those. So the output from each of these is wired to an input of the 8-input NAND gate. And it really doesn't matter which input goes where. These are, you could swap these any ways you want, because all these inputs, they all have to be high in order for the output to be low here. And we can see that if we look at the logic diagram for that chip, which is here. This is the 54 HCT30. You can see these are all high. If they're all high, this goes low. And if any one of them is low, the X means I don't care about it, because if any input is low, it doesn't matter what the other input is. The output is going to be high. And that's perfect for us, because we want that output to connect to this pin on the clock circuit. And so this input here, when this is low, the clock will stop, and when it's high, the clock will run. So let's make those connections. So this is the control output that we want there. So that's connected. Here, let me zoom this out. There we go. So there you can see that I've connected that. And then we also need this clock circuit input to connect to the master reset on the counter chip. And since this is kind of I would call it like, this is like an added feature, I think, to the clock. So like this is the Ben Eater clock, and this is the Scott DeVos counting circuit for it. And so I'm just going to put those together, and I'm going to wire them up here with power together. I'm going to set this to run at a fairly high rate. Now, I don't know if you can see, but I have set those switches. Let me get this wire out of the way. I have set those switches to 11110010. So let's take a look at that. Convert 11111010 to decimal. Okay, let's use Google for this. Convert 11110010 to decimal. Uh, there we go. So you can see that's 242. All right, and that, if you recall, that is one of the important numbers on the horizontal sync. 242 is the number of pixels, is one of the numbers of pixels. That's the end of the horizontal sync pulse. So that this should count up and keep that number and keep this lit when it gets there. It should halt there. So first of all, let's just check that this halts it at all. Let's put the power in. All right. And then this is not currently counting, but let's, oh, I forgot to mention one important part of this circuit. Here I have a button that's normally tied high, and it is connected to the reset on the counter, so that when I push this button, it resets the counter to 0. So I'm going to push that right now to reset the counter to 0. All right, and now I'm going to start the clock. Wait a minute, why did it not start? Something is wrong. That output should be high. Should allow this to run. Clock output to there. Let's just disconnect this and see if it runs. No. Got power connected correctly. Power jumped across there correctly. All right, I found my problem. I had plugged this into this input instead of here, which is where the clock input is. So that was my problem. Now the other thing I want to do is I want to adjust these switches so that we don't have to count such a high value. Oops, I started that counting. So let's start with something like counting up to 8. So this should stop the clock after it's pulsed 8 times. I'm going to clear it by pressing that button. And then I'm going to start the clock. 1, 2, 3. Clear. 4, 5. 4. Oh, yeah. Here you see I've actually set 4, not 8. So this should count to 4. 1, 2, 3, 4. And that's it. It doesn't count anymore. Reset. 1, 2, 3, 4. No more. I meant to do 8, so let's do 8. Reset. 1, 2, 3, 4, 5, 6, 7, 8. And we can do that for each of these to make sure that I've wired it correctly. So for example, if I do this, did I get that one on? Just do 1. That one might not be wired right. Let's do 2. 1, 2. So that worked. 1, 2. We did 4. We did 8. Let's do 16. 1, 2, wait. Stop it. Reset. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go. It worked. And I'm not going to check the other ones just yet, but I do want to figure out what's going on with the one. Oh, by the way, if you notice that if they're all off, it just always runs. Oops. Or does it? No, I've broken it. Let me get rid of the hotline. Oh, there we go. It's running. Ah, actually, what happens when they're all off is it doesn't run at all unless it's already started. Because it's at 0, it matches 0, so it's not going to pulse at all. If we could get it started, then it would count until it ramps all the way through, all 256. I'll speed it up, and then it'll go out. There you go. Now, I'm a little concerned about why the 1 isn't working. Let's see if 3 works. 1, 2, 3. All right. Slow that down. 1, 2, 3. 1, 2, 1, 2, 1, 2. Okay, so the 1 isn't working. So I'm going to have to solve that. All right. I have solved the problem. Let me just check my sound levels a minute. Okay. So I've solved the problem. The problem was simply that this switch is a little hard to move. That's the last one. I just wasn't getting it all the way in there, so it wasn't going. The other problem I was having was that this switch wasn't being debounced. And so if I were to push the switch and the bouncing would happen across the time when a clock signal is changing, which is fairly likely to happen if you're running the clock at a fairly high speed, then it might get an extra reset in there. And so, what I had to do was, what I did was I put a 1 microfarad capacitor here, and then I put a 100 kilo ohm resistor here to drain the capacitor. So what happens was when I push the button, the power or the current immediately goes high on this capacitor because it charges right away, and then it slowly bleeds out through this resistor. And I've chosen these values so that it takes about 1/10 of a second. So when I push the button, it stays high and then slowly decays. Let me show you what that looks like on notebook paper. So what I've done is I've got 5 volts tied through a switch, actually a push button switch, which is represented like this. And then it's tied through a normally open switch, and then it goes through a capacitor, and then it goes through a resistor to ground, and I take the signal off here. So this is the signal here. So when I push this button, current can immediately start charging this capacitor, and it charges it almost instantly right up, because there's very little resistance in these wires. So it charges almost instantly up to 5 volts. So the signal kind of looks like this. Here you can see it's sitting at ground here, and then I push the button, and it jumps almost instantly up to 5 volts. And then when I release the button, it'll stay there as long as I'm holding the button. When I release the button, it will start discharging, and it'll discharge in normal, exponential fashion like this. And once it gets down to, say, this voltage here roughly, then it goes low. And so the time I hold the switch plus this time here is how long it'll be before it goes low. And this is, I've chosen the time constant, so this is about 0.1 seconds. So it will go, I hold the button down, it goes up, it holds while I'm holding the button, I release the button, and it starts discharging through the resistor. And when it gets down below the certain level, then um, the well, then this NAND gate or this NOT gate will switch from high to low, and so then it'll allow it counting again. So that's it'll finish the reset. So as long as we're in this range here, that's the reset range, because the NOT gate that this feeds into will go from holding will go from have I done this right? Yeah, I'm sorry. I've got the connection here. This is all wrong. The connection is like this, and that makes sense. So this is being held low because the charge in the capacitor yeah, let me restart this whole description. This part is right. And as you can see, the signal is connected directly to the master reset. So this hangs out low until you press the button. And while you hold the button, it's high. And while it's high, the reset, the counter is being held at 0. And it stays that way until you release it. And then as this falls, eventually this will fall to where this guy decides it's okay to start counting again, and it starts counting. So the 1 bit is set there. So I set this for clock, and I press that, and you can see it goes 1 time. And so I've got that set up for yeah, 1, 2, and I think we tested up through like 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Boom. So that's just what we want. This is the number of counts that we specify in binary on these switches, and then it will stop the counter. So let's apply that to this horizontal sync. So we want to test the 200. So what we need is 200 in binary. So let's go back to Google. And let's say we want to convert 200 to binary. We could do this by hand or on a calculator, but I find it easier to show it to you doing it right here. So what we want is 1100 1000. So let's set that. 1, 1. Oh, let's turn it off while we're doing it. 1, 1, 0, 0, 1, 0, 0, 0. All right. So now we have. I didn't show you me doing that. Hold on. I just used a pencil to set these 1, 1, 0, 0, 1, 0, 0, 0. Comparing that here. 1, 1, 0, 0, 1, 0, 0, 0. So let's check in again. 1, 1, 0, 0, 1, 0, 0, 0. So that should count to 200 binary. All right. So let's hit reset, hit the clock, and then we'll see how it should stop with this LED lit. So clock. And I'm going to speed it up. And it didn't work. Let's try it again. Reset. Well, that's not good. Oh, you know what would help? I have to hook the clock signal, instead of right now it's being clocked here by the 10 megahertz clock. I also should hook up power to it because there's no power going to it. And I have to hook up the reset. Well, no, I don't need to do that. I don't want to do that. I just want to hook the clock up. So let's do that. Let's hook the clock here. Let's stop that. And let's set it, instead of using that clock, we're going to put the clock here. All right. And now this should do the job for us. So let's reset. And oh, we want to be able to reset both resets. The only problem is we've got this reset set up here. So so you see I've got this set up for doing at the end of the front porch or back porch to do the reset. So let's take that out. Get that out of the way so that we're not trying to both reset and not reset at the same time. Then let's run the reset from here over to here. So now when I press this button, this should reset both of these counters. So they're both reset. And now we're going to start the clock. I'm going to switch this to clock mode here. And it's counting. Oh, I still forgot to connect the power. So let's do that in a minute. Disconnect power there. All right. I'm going to connect up plus to plus. Minus to minus. Put in the power, reset, and start the clock. There it goes. Check it out. I'll reset it again. It's counting, and boom, it stops at 200. So I've got the 200 one wired correctly anyways. So now let's stop the clock, and let's change this to 210. So let's go back and ask Google to convert 210 to binary. And there we go. It's 11011010010. 11010010. There we go. All right. So I've made those changes to the switch. And so let's stop the clock, reset, just run the clock. Try it again. There you go. You saw this one. I hope you saw this one flash. Let me see if you can see that video. I'm going to run it again. You saw that one flash, and then that one lit up and held there. So now it's holding at 210. So that tells me that I wired the 210 one correctly. All right. So then what we'll do is we'll stop the clock, and we're going to change this now to 242. So that's 11110010. So 11110010. Is that right? Let's check that. 11110010. So we've got that set correctly. So we're going to reset, and we'll start the clock. Let's try it again. There you go. So you can see when I run it, both of these flash, and then that one comes on. Flash, flash, and that one's on and it holds there. So 242 is wired correctly. So that works. Now let me stop the clock again, reset to clear that. And now we got a little bit of a problem because we want to count up to 264. But we have only got 8 bits, and 264 requires that 9th bit. But if you recall, we're not worrying. We have the same problem with this. This is an 8-bit AND gate. But if you recall, Ben showed that it doesn't matter if we have something that both fires on 264 and 265, because we're never going to get to 265 because we're going to have this connected up to reset it when we get to 264. So really, we can set this up so it can count to 264 or 265. And how would we do that? Well, that just means we can ignore the Q0 bit in favor of the Q8 bit, right? So if I look at this, if I convert 264 to binary. I need 10000000100, or that could be a 1, that'd be 265, and what we're saying is that that's fine. So what I need to do is, what if I repurposed my my 0, or Q0, the ones bit, and replaced it with Q8, right? That's the 256 bit. And how would we do that? Well, let me go back to here. Here's what we're going to do. Let me get these wires out of the way a minute so you can see what I'm doing. All right, let me turn the power off. Okay, so what I'm going to do here is I'm going to take out this brown wire that connects Q0, and instead I want to connect that to Q8. So Q0 is there, and I want to connect that instead to Q8. So I got to look up where Q8 is on this chip. So let's go back to the sheet, and we can see that Q8 is the 13th pin, which is the fourth one from, or the third one from the power pin. 1, 2, 3 from the power pin, Q8. So let's look here. 1, 2, 3 from the power pin is Q. Let's look at that again. Seems not right. Fourth pin. Yes, 1, 2, 3. Oh. I'm sorry, it's Q9 that we need, right? Because, no, Q8 is 256. Oh, these are labeled differently. These start Q1, Q2. I'm used to starting Q0, Q2. So, all right, so I've been saying it wrong this whole time. This is Q1 and so forth. So I need, if you start with 1, then what I need is Q9, and that is pin 12, which is the fourth pin from the power pin here, pin 12, right next to the reset. So what I need to do is plug this in right here next to the reset there. Hold on, let me show you. So you can see I've plugged that in right there next to the resistor that that holds up or holds low the master reset. So that is going to allow us to count to 264 or 265, but we're going to stop, of course, at 264. So let me stop the clock. Let me run this. There we go. That's the master reset from our master reset button, and I am connecting the clock to the clock pin. All right, and I'm also connecting the clock to the horizontal sync clock and the reset to the horizontal sync reset. And I'm going to power it up. I'm going to reset both. Oh, I have to reset the, got to reset the pins then to zeros. Remember, we're moving this bit, the 256 place, down to the ones place, what I've been calling Q0, but what our chip calls Q1. So we need to set this up so that the 0 position is a 1. Here you can see, hopefully, 0 position is a 1. And then we need all the other 0 except for the 1, 2, 4, 8th place. So 1, 2, 4, 8th place is a 1. And we need all the rest to be set to 0. And remember that this 0, this ones place, or 0 as it's called there. If I show this a little, let me autofocus here. I think that'll help. So this bit is set to a 1. This is 0. That's a 1. 0, 0, 0, 0, 0. But remember, this is actually, because of the way we rewired it, the 9th place now. So let's start that and see if that works. So I'm going to reset, hit the clock. It's counting. Boom, boom. It seems never to work the first time, but the second time it seems to work. Uh, reset. Hmm. Reset. There. Oh, it didn't stop it though. Okay, so something's wrong. All right. Let me figure out what's wrong. I'll get right back to you. Okay. I figured out what I did wrong. It was real simple. You guys probably noticed. I put in the fours one up. It was turned on, and the 8 was off. So I fixed it now. So this is the right one. This is the 256 place. 256 plus 8 is 264. So this should run now. So let's clear it. Clock. And like I said, it never seems to work the first time. Let's clear it, and there it goes. So do it again. I don't know if you saw that, but they all fired, and then it stops on the 264. All right, so this board is done. This is the horizontal sync board. Just remind you that minor changes I've made from what Benator does is that I'm using a 12-bit counter here instead of three 4-bit counters. And the final reset, I'm having to change using a spare NOT gate because this resets on a high voltage instead of a 0 voltage. And I also wired these LEDs in reverse of the way he does so that they turn on when the signal from the output from the NAND gate is low. So let me disconnect this and reconnect this wire from the 264 counter. And that board's ready to go. I'm going to, I haven't yet made the vertical sync board, so I have to do that yet. And then I will get back with another video. Thank you for your time. I really appreciate you watching. If you liked what I'm doing here, please like and subscribe. And if you want to be alerted, click the bell. I'm just doing this for fun, but it's nice to know if you're appreciated. And thank you very much for your time. Oh, one quick thing. You may have noticed that I'm not really editing these. I'm starting and stopping the video when I want to take time to do something, but I'm not editing them. I'm just putting them out there. I kind of want to let everyone see how the sausage is made well when something project like this is done. And if things don't work right, or if I say something wrong, I'm okay with that as long as I correct myself on the video. So please also let me know if I've done anything wrong or said anything wrong or said something in a way it could be worded better. I'm just doing this as a hobbyist, and I would also like to get better. So we can all teach each other. Thanks again for your time.